today is going to be an interesting lecture, to say the least. I decided to give like a lecture that cuts across a bunch of different applications in robotics and language modeling. So it will probably be mostly incoherent, but if there's parts that make sense, I'll be pretty happy. So there's this sort of old idea in robotics called model predictive control. Drew likes to say there's two things that make the world go round. One of them is model predictive control. The other one is PID. So it's really sort of like a foundational building block in the way most kind of engineered systems actually work in the real world. As of late, something called test time scaling has become really popular and in vogue to discuss. If you guys have heard of things like O1 or O3, these sort of like LLM reasoning things, there appears to be this ability to train a model such that you can expend extra compute at inference time to get better answers. And I think these things are very related in a lot of senses to sort of kind of more foundational ideas, and that's what we're going to talk about today. So I'm going to first kind of present things kind of in the most general form, which I would say is model predictive control. I'm then going to try and give you guys an argument for why kind of looking into the future should actually improve performance, or how much it should improve performance. After that, I think I'm going to kind of give you guys like a zoo of different algorithms that basically fit under this overall template and talk a little bit about different ways they've applied to different problems. And then kind of I'm going to talk about how we can sort of close the loop and iterate this process to actually sort of improve the base policy, which is sort of the thing that leads to the sort of state-of-the-art performance. If we have any extra time, I spent a bunch of time last night going through some rather complicated proofs on how we could interpret all of this as really just like a finding operation. I don't think this is a terribly useful thing to know. It's really cool though, so if we have any extra time at the end, I'll go through it. Okay, let's go ahead and get started. So start off with maybe the first question that is pretty natural, which is like, what is model predictive control, or MPC for short? Has somebody used this before? There's at least multiple people in the robotics department here, so someone should have. Can someone tell me what it is? Yeah.
You have an imperfect model of the thing you're trying to control, or you have a transition model, I guess, and you're trying to plan based on your current state. Usually you have to replan because the model is imperfect.
Yeah, perfect. So let me just write out what Bart just said in more math. So we're going to say MPC is, roughly speaking, the following process. So for each time step in a problem, so for each AP in H, what we're going to do is the following. One, we're going to plan, and I'll say what this means more formally in a bit, a sequence of K actions starting from the state, so starting from stage, in either a perfect model, like a perfect simulator, or some sort of like approximate dynamics model, TPAT. And I'm going to call this a twiddle H to H plus K. So by this, you can think of this as sort of being like, does anyone remember the term for when you can like query your dynamics anywhere? There's like a term for this. We have different axis models. No, so it'll be a generative model axis. So remember we talked about how there's like trace models where you have like a whole trajectory or things like this. Generative model means I give you a state, I give you an action, I can give you an example of the next state distribution. So you can imagine I have a generative model axis to my environment, or I have some sort of like earned model. So the sort of stuff we talked about, I guess, 2 lectures ago. Then what we're going to do is we're going to execute the first of these actions. In whatever the real world is, so in T star. And then we're going to go back and do this at every step. So at every step, we're sort of planning out 8 steps inside our model, or maybe a perfect simulator, executing the first of these actions, actually taking a step forward in the real world, and then replanning over. Let me make this a little bit more visual. So we're going to have some state, let's call it S naught, we start from. Then what we're going to do is try out basically different sequences of actions we could take from this state and see what happens. So you can think about maybe this being, some sequence of actions. Let's call it A0 through K prime. And you can imagine that if we have this sequence of actions, we could, evaluate them in a simulator and see where we end up. So maybe this gives us, when we execute the first one, we get some S1 prime, some S2 prime, and we go all the way to, let's say, some SK prime. And maybe we see that this state SK, we look at it, is actually kind of bad. So maybe we can, okay, maybe this isn't the overall outcome we want. So if we wanted to, judge the value of, a plan, right? We sort of need to include two components. Both, what happens over the first K steps, and then what we expect to happen in the future. So kind of in the more traditional reinforcement learning notation, we might do something like we look at the reward, we see at state S1 prime. I'm going to assume all rewards are just state dependent for this lecture. It does not actually make a difference. We can add in S2 prime here, and then we can add some sort of, let's say, a terminal value function estimate here. Before we go on, why do I need to add this on? Why can't I just look at the sum over the first K steps? Yeah, exactly, right? Because just because I did well over the first K steps, it does not mean I ended up in a position that was really good in the future, right? It was like me last night. I was feeling really good until around 3 a.m. when I was learning a new thing, and then at 3 a.m. I was like, wow, I've ended up in a bad state. So just in words, we need a terminal value estimate to not be too greedy. Okay, so maybe that time it didn't work, but we can do the whole process again, right? We can just pick another sequence of actions. Let's call it A double prime 0 through K. And we can again evaluate us in the simulator, see all the states we ended up in, right? S1 double prime, S2 double prime, eventually get to some SK double prime. And maybe this state is actually pretty good. And then we could think about evaluating this whole kind of plan, right, of S1 double prime plus plus the reward of S2 double prime, going all the way till we get to the value at SK double prime. Okay, so let's say we think that this kind of plan seems like a better one, right? So then what we do in MPC is we say, okay, I'm going to execute just the first of these actions. And you can think about doing this in the real world to get some S1 prime, or S1, I should say. We're going to say execute this AH in T star. Okay, so we chose this path, right? Does this state and this state need to be the same thing? Why or why not?
The environment could be stochastic.
Yeah, exactly. So if our environment was perfectly deterministic, right? If I said I was going to do this, I'm going to end up in the same place, right? But oftentimes in practice, our environment is stochastic, or at least our model is inaccurate in some way. And that's why we want to do this sort of replanning, right? Because we're going to end up in a state we didn't actually expect to end up in. We want to use this new information to reinform our kind of search process. It really depends on the application, but for example, and I'll get into this in greater detail later on, but for things like language models, right, because you're just appending tokens, you always kind of end up where you expect to, so there's no stochasticity, so there's sort of limited value in replanning. Versus for kind of real robot systems, especially ones with sort of dealing with sort of, let's say off-road driving or things like this, there's a lot of value in sort of replanning. So maybe just to write that out, I would say the point to take away here is that S1 is not necessarily equal to S1 double prime under stochastic dynamics. And this is what makes us need to do replanning. I'm now going to write out a little bit more formally what the sort of planning optimization problem I'm going to be solving is. There's a bunch of different versions of this that you might have seen in other courses or in the past. I'm just going to pick one that I think is kind of convenient for analysis. And it's that we're going to say this A, h to h plus k proposed is going to be the argmax over actions I could take the next k steps starting at step k. The expectation under whatever condition dynamics I'm using. I'm going to do the sum from tau equals h to h plus k of the reward at that step. People sometimes call this a stage cost, plus that sort of terminal thing, so s h plus k, conditioned on a h plus k. So when we talk about planning, this is what I mean. People will sometimes call this optimal control, other things as well, but loosely speaking, these are all the same thing. So I'm going to now argue why this is actually a good idea. But before I do that, does anyone have any questions on like the actual process or the algorithm we're analyzing?
Where do value estimate come from?
So that's a really good question.
This is like V star.
Yeah, so good question. So I'm going to be a bit hand-wavy about that right now. I'll get into it in greater detail later, but I think that's a really good question. In practice, often you have some sort of trained value function or a heuristic that you use to sort of estimate the kind of cost to go. Alternatively, what you can do is just unroll for long enough inside your model that like basically if you assume discounting, the future cost is bounded because of the sort of powers of gamma. Other questions?
Is that what symbol is that in the expected value?
Where in the expected value?
The first subscript.
Oh, tau, sorry. Yeah, no, that's totally fair. Basically, I'm going to use t for iterations of the algorithm, so like tau seemed like a natural thing to use there. Yeah, please ask me if you have no idea what a symbol is. It also might be that I don't know what it is, but I'll do my best. Yeah?
Just choose the first action based on this arc.
Yeah. So kind of like what we're saying over here, you pick a full sequence of like a, h plus k, then you execute the first one.
It is like maximum over the last actions and argmax for the first one.
Yeah, you could write it that way. Yes. I was thinking of it, you actually take the argmax and just execute the first one, but yes, equivalent to what you're saying. Yeah, definitely. Any other questions? Cool. Okay. So now let's talk about, how good of an idea it is, or how much this is actually biased, right? So I'm going to go through what I think is maybe the usual version of this people proof, and I'll do a slightly fancier version after this. So let's say we consider some policy pi with value function v pi. So we can write down something, I'm going to call it pi plus 1 of some state as being the argmax over actions of the reward at that state, plus when we take the expectation over s prime drawn from t of sa of the value function of pi at state s prime. So you've hopefully seen this before sometime in this class. What did we call this before? Does anyone remember? So I have a policy, I want to make it better. What is that called? Yeah. specifically policy improvement, right? I have some policy pi, and I'm saying, okay, I want you to basically look one further step in the future, and I expect this to improve the policy, right? So this is just policy improvement. And you can imagine doing this again, right? In a sort of a recursive fashion. So R2 of S is going to be the R max A of R of S plus the expectation over stage drawn from T of S A of V pi plus 1 of S prime. And just inside this, remember that this guy here is equal to the max over actions of R of S plus the expectation over S double prime drawn from T of S A of V pi of S double prime. So there's this sort of like unrolling thing I can do where every step, when I do this sort of policy improvement thing, I'm really kind of bootstrapping on top of what I had before. I think Stephen mentioned this in his lecture. Does anybody remember how we proved that this process, even though it's a local improvement, actually leads to a global improvement in terms of performance?
A performance difference lemma?
Yes, okay, exactly. So I'm gonna write that out just so we're all on the same page. So we're gonna say that J pi 1 plus is minus J pi. We can write this as the expectation over trajectories drawn from pi plus 1 of the sum from little h to big H of q pi of sh ah minus the expectation over a prime drawn from pi of sh of q pi of sh a prime. And so then I think what we're going to do next is we're going to say, okay, what actually is this AH, right? We sort of defined it as coming from this pi plus 1. So by our definition up there, we know it's the maximum, kind of the best action we could take at this step, right? So we can expand this out to be basically the same thing, but with a max stuck in. So h to big H, max over a, q pi, sh a, minus this, the same thing we had before. So a prime drawn from pi of sh, q pi, sh a. And sort of like we kind of mentioned in the lecture from a while back, this is bounded away from 0 or non-negative. And this means that overall, because we're taking an expectation over non-negative quantities, this whole thing must be greater than or equal to 0. So we have improvements. This sort of like ringing bells, everyone like vaguely remembering this thing? So you could essentially make the same argument for, pi plus 2 over pi plus 1. You can do this all the way down, right? So basically, it's pretty easy to argue that each of these policies, when you do policy improvement, will do better, or at least not worse, than the prior policy, right? This is sort of the monotonic improvement thing we sort of proved for exact policy iteration style methods. So that's true, right? But I think the thing we sort of didn't talk about in the past, right, is exactly how much better you will get, right? And that's what I'm going to kind of go through now. But you should really think of this sort of like thing we're doing here, this one step of policy improvement, as doing MPC, but just one step of MPC, right? Like my horizon inside the MPC thing, like k is equal to 1. That's what this is. So all MPC is really, if you have a really good world model, really good terminal value function estimate, it's just like multiple steps of policy improvement. Any questions about this? So, This is a proof I mostly stole from Wen, but I redid it myself. So if there's any errors in it, these are my fault. So I'm gonna make the sort of K-step version of what we just talked about a bit more formal now, and I'm gonna try and argue what the actual increase in performance you get from doing K-steps of look-ahead is. So let's say we define the K-step look ahead policy as pi plus k of some state sh as being the, I'm going to be a bit sloppy and write argmax over the next k actions, but like you said, it's really argmax over the first one, max over the rest. K h plus k expectation under, for simplicity, I'm going to do everything under the ground truth dynamics. Otherwise, you would basically tack on an extra term because the simulation lemma of this guy right here. So from tau equals OH to h plus k. And we'll also introduce a discount factor here because it ends up matter in the analysis. So gamma to the tau r s tau plus the end of this gamma to the k v I s h plus k. All of this conditioned on starting on state sh and taking actions a h to h plus k. So if you think about doing like rollouts in your simulator, right? Those are essentially like a single sample estimate of this quantity. I'm doing everything in expectation here just to avoid having to do any finite sample analysis. But you could imagine if you just execute the same sequence of actions over and over in your simulator, you'd kind of see something that converged to this on average. So I'm going to define epsilon as basically being the worst case deviation between our starting policy and the optimal policy. So max over S and S of V star of S, so the optimal value function minus R's, V pi of S. And I'm going to divide this over H. The reason I'm dividing this by H is because in general, this quantity can like scale with the horizon, right? Like there could be some state where we're really, really bad, but the optimal policy is really good. So I want to have, in general, your epsilons be like kind of horizon independent. Otherwise, it's sort of hard to compare things. Then the claim we're going to prove is that j pi star minus j pi k plus is going to be bounded by something that looks like epsilon times h times 1 minus gamma to the h all over 1 minus gamma to the k.
Discount is that.
Yes. Okay, so just to give you guys some intuition for, yeah, go ahead.
Sorry, what does it say beneath the max? Is that epsilon subset S?
Sorry, that's my bad, thanks for asking. That's just S and S. So I'm saying, okay, right, max over all states in my state space. Yes, thanks for asking. Okay, so I think when you look at this expression we have here on the right-hand side, that's very unintuitive. I don't actually really know how much of an improvement that is. Let's just say, because this is a thing that's kind of common in practice, gamma was something like 0.99, and k was something like 10. And our horizon was actually, let's say we did the infinite horizon version of this, right? Then we know this, the thing we would see for the infinite horizon version, right, would be just the thing Yuta was mentioning, so 1 over 1 minus gamma. And this, if you think about gamma being 0.99, is like 100, right? Versus here, we're going to get 1 over 1 minus gamma to the k, right? Because that's what we have in the denominator here. And this is roughly 10. So This is not exactly true, but basically by doing k steps of look ahead, you essentially get the performance you would have gotten if your like sort of errors were like, divided by this sort of k thing. And this is sort of like this is a kind of a fairly non-trivial sort of increase in performance, right? Because I'm going from my errors being scaled by 100 to my errors being scaled by 10. So you effectively get a 10 times better performance bound by doing 10 steps of look ahead. Cool. So before we actually do the proof, which is similar to things that we did a few lectures ago and you did in the last lecture, does anybody have any questions about the actual statement? All this statement I think is trying to say is that if I do this sort of case steps of look ahead on top of my base policy pi, I will improve in performance over this policy with something that scales with the number of steps of look ahead I do. Yeah?
Sorry, in the big O, is that the first one is a minus and the second one is a times?
No, everything is times. So it's epsilon times h times inside the little parentheses 1 minus gamma to the h all over 1 minus gamma to the k. Yeah. Good. Other questions?
This is like discounted but finite horizon.
Yes, correct. I do think you need the discount factor for this style of analysis to work. You can do it in the infinite horizon version as well. I just prefer finite horizons. Was there a question? Okay. So, we're going to do the same sort of thing we did for the proof of the simulation lemma. We have these two terms. We're going to add and subtract of the cross term, cancel things out, form a recursion, solve that recursion to get the final thing. So, in slightly greater detail, we're going to say that B star of state S minus B plus of k of state S. I'm using just v k plus to mean the value function of pi k plus of some state, let's call it S1, 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 is going to be, we can sort of just expand this out in terms of just the definition of what a value function is. So I'm going to expand it out into the discounted cost for the next k steps plus the value function k steps into the future. So we're going to get the expectation over sum from little h to big H of gamma to the h of r sh plus gamma to the k v star of s k. All this conditioned on pi star. And then we do the same thing for our policy pi k plus. Sorry, a little bit messy there, but basically it's the same term. I'm just swapping out the value function for the value function of pi k plus and saying I'm picking actions according to this k-step look ahead policy. Then what I'm going to do is I'm going to call this term A and this term C, and I'm going to do an add and subtract trick. So what I'm going to do is basically say that this is equal to A plus a cross term. So the expectation over sum from, oh, also, this should not be the sum to big H. That's my bad. This should be the sum to K. Because I'm going to be expanding this out K steps in the future. Does that make sense? So I'm basically saying here, I'm going to, instead of expanding this out all full H steps of the problem, I'm going to just do K steps of look ahead and have a terminal value function, K steps in the future. Make sense? Good. Okay. So let's write that out. So HK gamma to H R of h plus gamma to the k v star of s k. All this conditioned on pi k plus. Notice how there's sort of a mismatch here where I am, say I'm taking actions according to pi k plus, but the terminal value function is v star. Then I'm going to do this, I'm going to subtract this term out. So I'm in net, I'm doing nothing. I'm from little h to k of gamma to the h r of sh plus gamma to the k v star of sh, all conditioned on pi k plus plus c. So these guys are exactly the same thing, just like signs, right? So I'm just adding and subtracting, they sum to 0. So, okay, we have this set of things here. Now, the sort of key step in this proof is realizing that two terms cancel. Specifically, this term here and this term here cancel. Can anybody tell me why that's true?
You are picking actions corresponding to the same policy, so the reward that we get will be the same.
Exactly, right? So I'm picking actions, the first k actions according to the same policy, right? So these two expectations, I can break this up into two expectations by linearity of expectation, and then this term and that term are the same, even though the terminal value functions are different. I can sort of remove the first k steps of what we had. So if you think about what I'm doing here under the hood, I'm effectively doing a k-step version of the proof for the performance difference lemma. So, okay, so let's cancel those terms. Then what we have left is the following. We're going to have, I'll put these in brackets, a minus the expectation of sum from little h to k of one of the cross terms, right, the one that's left. So gamma to the h, r of sh, plus gamma to the k, v star of sh, all of this conditioned on pi k plus. Then I will have the final matching term, which I haven't touched, which is going to be, or sorry, I guess I'll have the difference of the two things that's left. So I guess I'll have the expectation over gamma to the k of v star of sh plus gamma to the k of, or sorry, minus gamma to the k of v k plus sh conditioned on me picking actions with pi k, right? What I'm doing here is I'm just copying this term from above down here. And if you think about this term and this term canceling out, what's left, right, is just the discounted value function I would get k steps in the future had I chosen k actions according to this k step look ahead policy. Does that make sense? Cool. So now I am going to do two things. The first I'm going to do is swap out this. We don't actually know what this V star thing is, right? But we do have a guarantee that wherever we are in the state space, this V star is bounded by epsilon times h, right? So I'm going to replace, and it doesn't depend on what SH we're in, right? So I'm going to swap out this guy for V pi, and I'm going to pay a cost epsilon times h. And I'm going to do that in both this term A and this term here. So I'm going to pay 2 epsilon h multiplied by the discount factor of gamma to the k. So in slightly greater detail, what this means is this is upper bounded by the expectation over the sum from little h to k of gamma to the k R of SH plus gamma to the, sorry, not gamma to the K, I got gamma to the H, R of SH plus gamma to the K, V pi now instead of V star of SK. All this conditioned on choosing actions according to pi star. Then what I'm going to do is I'm going to get the term where I have the sum to the K of gamma to the K R of SH plus gamma to the K d pi of SK, conditioned on taking actions according to pi plus of K. And then I'm going to have this remainder term we had above, which is going to be the gamma to the K times the expectation of V star of SK minus VK plus of SK, conditioned on me picking actions according to my K-step look-ahead policy. Plus, you know, the thing I have to pay for switching from V star to V pi, which is 2 epsilon H gamma to the K. So the sort of other sort of slick trick in this proof is that this thing inside the brackets here, right? This is exactly what I defined pi plus K as being the optimal policy for, right? It is like literally trying to maximize this sort of K-step thing, right? So what I can do is I can actually say that this will be upper bounded. This will be upper bounded if I swapped pi star for pi K plus. And then these two terms are the same, so they cancel. And then this leaves this thing over here. So what you end up getting is basically a thing where at every step of this sort of recursion, you pay 2 epsilon H gamma to the K. And then you pay gamma to the K times this recursion K steps in the future. So you can just unravel this recursion, right? And you will get something that looks like, or first, if every time I do this, I go K steps in the future, how many steps can I go in total? If big H is 10 and K is 2, how many steps can I go? Division. Yes, division, so 5. So at most I can go H over K steps of this process into the future, right? So what you end up getting is something that looks like 2 epsilon H times the sum from I equals 1 to H over K. Gamma to the K raised to the I, which is equal to 2 epsilon H times 1 minus gamma to the big H, all over 1 minus gamma to the K. So I don't think the details of this proof matter too much. I think that part of the reason, you know, I went through the simulation lemma proof in detail, you know, went through the proof in detail last time, I went through this proof right now. It's not because we expect you to memorize all these steps. It's because, like, if you ever read a reinforcement learning paper that has some theory in it in the future, I'm willing to bet this is essentially how they prove what their claim is. So it's good you see these sort of steps over and over again, right? So basically, they look like I do this sort of add and subtract thing, I form a recursion, I solve it, and that gives me the final performance bound that I want. The sort of, I think, the cuter thing I'm doing here is that I'm actually expanding K steps into the future rather than just one step in the future. And I'm utilizing the fact that I have a policy that was trained to be optimal for the next K steps. And that's what's sort of giving me this sort of improvement in terms of overall performance. I'm gonna get stuff that's much more applied now, but does anyone have any questions about this part?
Do you mind interpreting this bound slightly more? So the bound depend linearly on epsilon.
Yep.
And epsilon is this quantity as defined as like the difference, the error in the value estimate divided by h. Is this supposed to be small, like even when pi is like not super good?
Yeah, good question. So there's two questions there, right? The first is, okay, let's say I didn't do any look-ahead search, right? I just used pi, right? Then hopefully it's clear that our bound would be epsilon h, right? The value function at any state is bounded in difference by epsilon h. J pi is an expectation of this quantity over the initial state distribution, right? The total performance must be bounded by epsilon h. Wow, I didn't think the lecture was that bad. But the question Stephen was asking though, which is a good one, which is, okay, this epsilon, even if I scale by h, can be really, really big, right? Because if my starting policy is really bad, and I'm always doing terminal value function estimates according to policy pi, it means I'm not going to improve that much, unless I basically set k to h, in which case I'm actually just doing regular reinforcement learning at that point, right? I'm doing the whole exponential search thing. So in practice, what people do is they iterate this process. So they will update pi based on this thing. They'll basically use this sort of k-sub look-ahead policy as an expert and do dagger with it, and then iterate this process over and over again. This is usually called expert iteration. I'll go through this in more detail in a bit.
The pi itself also improved during training.
This is like the one-step version of it.
Thanks. And I guess in the limit when you push k to h, this bound is not tight, right?
I don't think so.
Right, because like when k is h, you're literally doing pi star, but like you still pay for epsilon h, and that's okay. So at some point,
Yeah, somewhere.
this bound is like not.
I think for one of these underground steps. Yeah.
Okay.
Yes, that's a good question. It's also because I'm being a bit sloppy with part of the analysis. If you do it in the infinite horizon version, it ends up being tight.
Okay.
Yeah. Other questions? Yeah.
You mentioned that when reading a reinforcement learning paper, the proofs would be similar to this, but could you maybe comment on like what the variation, where in these proofs variations would likely occur?
That's a good question. So I think it really depends on the specifics, but so there's a bunch of proofs for like tabular reinforcement learning, right? So things where we have a finite state and action space, and we don't, let's say, worry about really having like function approximation, like trying to learn the value function or have a learned model, something like this. We basically treat everything as a tape, right? For proofs that look like that, which are basically, I would say, proofs up to maybe the early 2000s, you will always see something that looks similar to this analysis in the sense that you want to argue that if I have a bound on something that is local, so for example here, just a k-step local look ahead, I have a bound on the terms of the overall performance difference between my policy and like some comparator in some sense. So the variations will be, for example, in how like local it is. So for example, here I'm doing k-steps of look ahead. In the simulation lemma, we instead said we did look ahead inside a model. And for example, you will also change the comparator. So here I did respect to pi star. Sometimes you'll do it with respect to like the base policy pi. You can do that proof as well. Sometimes, for example, you can imagine competing with an expert. Basically, that comparator will be where a lot of the other flexibility comes in. So I think it's both in terms of like what locally optimal means, and also in terms of the actual comparator you see. Does that make sense? Okay, good question. Other questions?
So what is the value function of states here? Does it depend on the time step?
Yes, good question. So yeah, all the value functions here should be indexed by time. I'm just being sloppy by not having a subscript. Yes.
So in that sense, does this bound really be meaningful? I mean, is that really an improvement? Because, so could it be like treated as you divide the right term by h and you got a new epsilon, and seems that it's bigger than the
Well, 1 minus gamma to the h over 1 minus gamma to the k is less than 1. So it's like I have a smaller epsilon. So think about the,
Oh, okay.
yeah, got it, yeah. The question is basically how much smaller the epsilon is as a function of the number of steps of look ahead that I do. Yeah. Other questions? Cool, okay. So enough math, cares about that. Let's go do something a bit more applied. So I want to talk about how, how would I actually solve this k-step look ahead problem in practice? Let's talk about a few different variants of this idea. So I'm going to bring back the sort of objective we were talking about earlier. So we had this thing that looked like, a triple h to h plus k is going to be the argmax over k steps, a h to h plus k, of the expectation under our transition dynamics of the sum over the next k steps, equal to h to h plus k of r of s tau plus v of s h plus k, conditioned on me taking that sequence of actions, right? H plus k. So if someone has taken maybe Zach's control course, does anyone remember what like a forward shooting method is? Yeah.
Before simulating the random gradients on the track.
Yep. So I would say what we're doing here is like fairly similar in some sense to people sometimes call it shooting method. So to see this, think about what the actual sort of problem we're solving here is under deterministic dynamics. So we're going to have some kind of r of s naught. Then the next step is going to be plus the r at the next step, right? So r of the transition dynamics of s naught, a naught. Then we would have the next step, right? So r of the transition dynamics of the transition dynamics of s naught, a naught, a1. So as you can kind of see, right, inside this actual thing, because I'm kind of enforcing, I'm always acting in a way that is like usable under the dynamics, I kind of get this sort of recursive application of this transition function. What that means is that this objective is really, really ill-conditioned, right? Like if you heard about like vanishing or exploding gradients, things like this, when you're like training like a sequence model, this is the exact same phenomenon. So it turns out that doing like, unless you're much more clever than myself, doing a first order method here where you take gradients requires a lot of extra care to make sure things work out well. So I'm just knowing that this problem, when I write it out this way, is sort of ill-conditioned. That's why for a lot of the things we'll talk about, at least in this course, everything here I'll be doing like a 0th order optimizer. So just sampling and seeing what happens, which requires sort of less smoothness assumptions on the actual problem. If you try to solve this problem via gradient descent, unless you had something like linear dynamics and quadratic costs, it gets very hard very quickly.
Ryan has a question.
Oh, yeah, please.
Is it v sh plus k and then a of h plus k?
Yes. So a of h to h plus k, yes.
Thank you.
Yeah.
So are you using 0th order methods to avoid reconditioning or non-smoothness of the landscape?
Yeah, that's true. I'm going to ignore that detail for this class. Good question, though. Okay. Let's look at this guy here. I'm going to basically note that oftentimes taking an argmax over all sequence of actions, even of depth k, can be really, really hard. So oftentimes in practice, you'll relax to sampling a bunch from some base policy, getting some set of, let's say, like m samples, and then basically argmaxing over this finite set of samples. So you can imagine this often being relaxed to something like argmax over a1 to an, where each a sub I is sampled from pi b, and I'm using just the vector notation here to mean the k-step plan. And this here can either be a learn simulator, a simulator, or some sort of learn world model. Maybe the last thing I'll note about this objective is that I've also been very vague about what this V is, right? So if this guy is V star, that sounds really nice, right? Like I know the optimal cost to go from this point, kind of hard to get, right? You could imagine this instead being V of some expert policy. If it's V of some expert policy, this is effectively a multi-step version of Dagger, right? Because if we think about Dagger, right, essentially we're saying pick actions that are optimal if the expert were to complete the rest of the episode, right? And this is basically saying, okay, pick actions that were optimal if K steps into the future, the expert were to complete the rest of the episode. And you can also imagine this being V of whatever your base policy is, and then this is just like a multi-step version of policy iteration like we talked about. And basically you can do proofs that look very, very similar to what I did earlier to basically encapsulate all these different things where you can basically take whatever kind of flavor of base policy you want and improve upon it in some way, depending on how good your value function estimate is in the future. Maybe the last thing I think is sort of interesting to note here, right, is let's say for the sake of argument, the dynamics are deterministic, right? And think about it as operating in some sort of like tree structured MDP. So basically think about like language where I'm just like appending a token and I can see the entire history of where I came from any sort of like sequence of things thus far, right? And let's also think about this being, we actually do the full planning problem. So not just doing it for K steps, I do it for the full capital H steps, right? Then you can think of this problem as basically searching through all paths through the tree from leaf to the roots, right? What you can then think about this sort of process as being then is that like, it's kind of like almost like a lazy version of that, in the sense that I only do this on the actual states. I should actually do this condition on SH, sorry. Condition on SH. I only do this on the states I actually encounter during my planning process, rather than doing it all ahead of time and sort of like saving it into a policy. So it's really like, people will often use words like lazy when describing things like this because it means you didn't pre-compute everything, you're doing it based on what you actually see at test time. Does that point vaguely make sense? Cool. So let's maybe talk a little bit about what are the actual algorithms people use to solve this sort of thing. I'm guessing these are things people have seen before, or at least someone in the class has seen before, so I'm gonna ask you guys to help me a bit out here. So the first is gonna be what I'm gonna call best of n, or BON for short. This is something people will use these days a lot for language models. Has anyone seen this before? Can anyone tell me what this is? Yeah.
I was guessing, don't you just generate like a throw response and then take the best on that perform like according to some metric?
Yeah, exactly. Nice. So best of n basically means I'm going to select A, 1 through capital H, so the full H steps in the future, like the whole problem, by taking basically an argmax over some finite set of things that were sampled from a base policy, of which there are n. So a n1h, all sampled from some base policy B, R of sh. And you can write this for language things, right? The terminal state here is really just going to be the concatenation of all the different tokens. So I think the thing you might naturally ask here is, okay, here I'm doing it over all 8 steps, and I'm not doing any replanning. Why is that okay here? Why do I not need to replan here?
There's no randomness.
Exactly, right? Because when I append a token, I actually do append the token. It's not like I say I'm gonna add the word the, and like the word apple appears magically, right? There's no need to do any replanning, there's no randomness, the dynamics are perfect in that sense. So I think a best event is like the simplest possible MPC algorithm with a perfect dynamics model, eliminating the need to actually do replanning. Then, if you have more of a robotics background, you might have heard about things like the cross entropy method. Or fancier variants of this, like MPPI, model predictive path integral control. I think that's what that stands for. Has anyone seen one of these kind of things before?
Basically sampling actions instead of using gradient base.
So do you remember much about how you actually like do the sampling for that process?
I think mine just prepare the action. And then the coefficient determine which action.
Yeah, exactly. So in like slightly more mathy notation, what we're going to do is we're going to sample basically some A1 through, let's call it K, 1 all the way through A1 through K. I'm going to use the same N here, drawn from some policy, let's say at round T of the algorithm, pi T. Then what I'm going to do is I'm going to pick the top, let's say X% of things, and I'm going to compute the mean for them. Let's say it's like mean T plus 1. So when I say like pick the top 10%, what I mean is, sum up the rewards for the next K steps, look at some terminal value function estimate and say, okay, I can order all of my N samples here. I'm going to pick maybe like the top 10%. I'm going to take the mean of those. And then I'm going to basically use that to update my sort of base policy. So I'm going to say pi T plus 1 of the state SH is going to be basically a normal distribution with mean mu T plus 1 and some usually fixed variance sigma squared. So if you guys remember for your like class competition things when you were doing the cross entropy method, which I think more than a few groups did, this is basically what you were doing, right? So I think of that as basically a slightly fancier version of best of n, where two things are different. One is that you're usually actually doing replanning in the loop. You're only doing it for case steps in the future, and then you like see where you actually end up in the real world and do replanning. The other thing that's different is that you are actually updating the sort of base policy this way, right? Like over here, we basically just sampled a bunch from it, and we're like, all right, we're done. Versus here, I'm gonna actually update what I do. So the next time I do this process, I can have a better distribution to sample from.
This is like mostly continuous action.
Yes, exactly. So I'm gonna swap between discrete and continuous a few times here, but this is usually done in discrete land, this is usually done in continuous land, right? It wouldn't make sense to like average the sentences you generated in like in terms of logins. That wouldn't work. Good one.
The top 90% is based on values.
So yeah, based on both the sum of the case steps of reward plus the terminal value estimate. Yep, and usually people pick like the top 5 to 10% to do the average there. I don't know if there's any sort of hard and fast rules, but it seems what people do in practice. Questions? Yeah.
What is your take on using gradient-based search heuristics? So I guess both of these are gradient-free, but for some applications, maybe you do have some really noisy gradients.
Yeah.
Is it typical to use the gradient?
I think it really depends on the application, right? So it also depends on how good your gradient is, right? So think about something where you have like some body moving in free space, right? Then I think like gradients are quite natural because everything is kind of smooth, right? But as soon as you have things like there's distinct modes of interaction, right? Like I have contact and then I have to have a very different thing. That sort of sharp sort of mode shift often leads to kind of non-smooth gradients. So it really depends on the problem, right? And it's really hard to say something general there. Like, a few lectures ago, we talked about things like Dreamer and like learn the world models. There, the difference from like the standard actor-critic thing is you actually also include first-order gradients in your update. So you'll actually differentiate through the world model and add that as an additional term. I usually think of this as basically being a bias variance trade-off, since that the first order thing is more likely to be biased because it might not deal with smoothness well. But it does sort of reduce the variance in the sense that like it kind of gives you a direction that is less dependent on the sampling noise. Yeah. Other questions? Cool. So to conclude, I'm going to give you guys a, let me think. Okay, I think I have time to talk about this. So I'm going to give you guys 2 examples of how you do this in discrete spaces rather than continuous spaces. So the sort of canonical classical algorithm here, which is due to Stephen's PhD advisor, is called sparse sampling. It's Kearns, Mansour, and Ng. Anything you'll notice in this class is almost every paper we cover has at least one author named Andrew on it. But the idea of sparse sampling is basically the following. I'm going to, from my current state, construct a kind of tree based on like trying different actions out. I'm going to then basically run Q-value iteration inside this tree. And as long as this tree is wide enough and deep enough, I get guarantees for the performance of my policy computed via doing value iteration in this kind of approximate tree. So the algorithm kind of looks like this. Basically, you start from some state S, and usually you think of trying each action out some number of times, let's say C. So let's say this is like a binary problem, so I only take actions A1 or A2, and let's say C is equal to 3 here. What I'm going to do is I'm going to try action A1 out 3 times. I'm going to try action A2 out 3 times as well. I'm going to end up in some states after I do this, right? So maybe over for these 2 times I ended up in some state S1. Maybe this 3rd time I ended up in some state S2. Maybe all 3 times I tried out A2, I ended up in some state S3. Then what I'm going to do is repeat this process at each state I ended up in, like 1 step down in the tree. So I'm going to do 3 things here, 3 things here. Draw this out very slowly, but hopefully you get what I'm saying. And I'm going to do this up to a maximum depth of h. So notice how I'm not like doing this for all possible next states I could end up in. I'm sort of being lazy here, where I'm only doing it for the next states I actually saw during the sampling process. So really what I'm doing here under the hood is I'm constructing some approximate MDP, M hat. Then, like I said, you compute I star hat in M hat. And I didn't want to do the proofs for this because it requires a bit fancier math than I like going into, but basically we can set C, so basically the width, the number of times I try an action, and H, so the depth of this tree, such that we have strong policy performance guarantees without a dependence on the size of the state space. So I think that's really the critical thing to take away from like why you would care about these sorts of things and why I've talked about things being like lazy or only being done at test time, right? That if you actually do like value iteration, policy iteration, right, you are doing it at every single state in your MDP, right? So as your state space gets bigger and bigger and bigger, this gets really, really hard to do. So one way we talked about dealing with this is function approximation, right? We had this sort of approximate policy iteration kind of thing, right? Another way to deal with a really large state space is you only do the computation for the states you actually see. So here, right, that's why I was noting that like I'm not actually doing it over all possible next states I could end up in from S. I'm just sampling a few times and seeing what set of states I get in. And this sort of means that you have an amount of computation that does not scale inside the unit space.
Sample from some action distribution.
So right now, I'm saying you're going to play each action explicitly k times, but you're asking exactly the right question. So, okay, so let's say we care about computing the optimal policy in this sort of like small MDP here, right? And we find out that when you take action A2, you end up in a really, really bad state every single time. Like S3 is just terrible. Is there a need for us to actually further expand S3 and try out things there? Probably not, right? Because we already know that the cost is so bad that things are just not going to be good in the future. So you'll notice here we're sort of doing a uniform sampling thing, where we're trying each thing out an equal number of times. This can be sort of like needlessly expensive. This is sort of a hard question, but does anyone know like a particular situation in which this sort of thing would be, this sort of extra expense would be kind of a really bad thing to have? Like what sort of problems, if I was doing this on, would it be a bad thing?
Could you repeat the question?
Yeah, so my question is, okay, so we brought up this point where we are going to sort of sequentially go through all these things, try each action like k times, see where we end up. This can be sort of needlessly expensive. We might look at the state S3 that's actually kind of bad. I'm asking, okay, but I'm still doing this whole process, right? Why is this actually bad?
States are very rare.
Yeah, so in particular, what I would say is that if you were actually running this on a robot or some system that has real-time, like time constraints, right? If you spend a bunch of time exploring the bad states, let's say like S3, and you don't fully explore S1 and S2 instead, you don't have good, what people will call anytime guarantees. In the sense that if I were to truncate my algorithm at any time step, I have good guarantees of performance. My point here is that like, okay, maybe you don't really care about sample complexity. Maybe you're like, okay, I can just sample a bunch, it's fine. But if you actually are doing this on like any sort of real-time system, right, it becomes a really, really bad idea because you will end up exploring a bunch and potentially wasting time, which is not good when you have to figure out what to do like immediately. Right? You know, those like CAPTCHAs you have to like solve sometimes, right? You know, a few years ago they had a bunch of these that like were, like reading like signs on the road. And the sort of theory I always like to have in my mind is that there's some Waymo car out there trying to figure out desperately what the sign is, and you have to figure it out very quickly. That's the canonical example of anytime planning in my head. Maybe just to connect this to something you guys have heard before. I'm guessing people have heard of Monte Carlo tree search before. Usually abbreviated to MCTS. And this is maybe the most natural way to try and address the things Stephen brought up, where rather than sampling each action C times, we do a more careful exploration strategy. So in this course, we basically have not really touched on things like exploration and like things like linear MDPs or bandits or stuff like this. So I don't want to get into this in too much formality, but roughly speaking, if you see that something looks bad based on the number of samples you've seen before, you stop exploring it and you start looking at things that still have the ability to be promising. So a little bit more formally, you can think of some sort of upper confidence bound style thing that basically says that rather than playing each action C times, you instead play the action that is the argmax over your current average of what happens in the future. So like your Q hat of SA plus an exploration bonus, which usually goes with the log of the number of times you've seen the state over the number of times you've played this state and action. So if you have taken a statistics class before, you might have heard about things like a Hufting bound. This is basically a Hufting bound, or sometimes called an upper confidence bound. So really you can think of this as sort of the sequential or recursive application of a bandit algorithm. If you haven't seen it before, don't worry about it. It's not something we really touched on in this course. I just wanted to note that the way you would actually want to do this sort of thing in a more realistic problem is not sample everything C times, actually do something a little bit more intelligent. And if you guys have heard about things like AlphaGo 0, or even the regular AlphaGo, this was sort of the core algorithm that went into them. Maybe to sort of close out the lecture, I will note a few things I think that are kind of interesting. So in this whole process, right, we kind of talked about doing this for like one step. So we have some policy, we do case steps of look ahead, and we essentially throw away all that computation, right? We don't necessarily have to throw away those case steps of look ahead. We can actually use that to update our base policy and kind of iterate this process. And this is usually called dual policy or expert iteration. And this is how things like AlphaGo actually work in practice. The analysis here is really beautiful, but it also is fairly involved, so I'm not going to go through it. But basically what you say is that for each, let's say, time step in your algorithm, so 1 to big T, so these are rounds of the algorithm, not time steps of the MDP. I'm going to basically do a local search around pi t to produce some slightly better policy. Let's call it eta t. And this is usually done via something that looks like multiplicative control. Then what I can do is I basically use Dagger with eta t as the expert to improve to pi t plus 1, and people will sometimes call this distillation, or like guided search or things like this. So I'm going to give you 2 examples of this that I think are particularly cool beyond the AlphaGo one. So the first is what I'm going to call V star for LLM reasoning. So this is like a pretty recent paper, I think from folks in Canada. But people rename a bunch of things over time. So to put this in kind of terms you've heard before, SFT, the blue bar here, is just behavior cloning. The third bar here, verification, is just best of n. So I'm going to sample a bunch and then rank it according to my reward model, pick the best. And you'll see that you get like a pretty big improvement here. Part of the complexity for this stuff is actually you have to learn the reward model. We're not really touching that on this in this lecture. We'll kind of get into that in future lectures. But then what you can do is you can actually distill the best of n back into the base policy. And the thing that's kind of interesting, right, is notice that when you do the search and just pick the best versus distilling it back into the base policy, there's actually a decrease in performance, right? So generically speaking, the only reason you want to do distillation is for like better inference time compute restrictions, right? So like here I only have to sample from the policy. I don't have to query the verifier like I do here. So like things like O1, as well, as far as we know, are basically doing something like this distillation thing, so they don't have to do the verification at test time. What you can do though is you can actually iterate this process. So what you can do is you can basically do best of n. You can feed into distillation, and then you can basically do another step of search. So if I had to put this in sort of like the notation I just used, I would describe maybe star here, a self-taught reasoner, as being like pi t plus 1, and distillation as being like eta t plus 1. So really, I think the best way to think about like, you know, the sort of like self-taught reasoner things you'll see people talking about these days is really just, you know, one step of expert iteration, and then the fancier versions of it are just like the next step in this whole expert iteration loop.
So that's more like, the last one is more like the dual policy.
Yes. I mean, I think that even star is like dual policy iteration, but it's like, usually you stop at step 1, but for V star, they're stopping at step 2. They're doing like an extra half step in some sense. And that's where I think the core performance gain is coming from. And then maybe lastly to note here, I'll just kind of close off with this. Example 2 is going to be sort of self-improvement things people talk about in LLM learning these days. And basically the core idea here is you do best of n with your reward function for the full sequence of tokens you generate to be basically the sum of the log probs for your current policy. Sorry, pi of the h conditional on sh. So basically what's kind of interesting here is rather than even having an external sort of reward function model, all this stuff, you can sometimes actually just use the logic of your policy, and this actually still works. So the reason that you should actually expect this to work right is we're actually doing like a more complicated inference procedure. We're not just sampling autoregressively, we're actually ranking the whole sample based on the total probability. And that can lead to improvement on various tasks. So I really think of this as, you know, the sort of best of n, aka the simplest version of NPC, just doing it with a particularly easily accessible cost function or reward function. I think that's it. I think we're at time. Yeah, thanks everyone.